Okay, so again, we're going to give you a lot of examples. This may be, unfortunately, hard to read. I'll try to get that thing fixed. So this is a paper from just a few years ago, and it had a bit of a difficult thing to stomach in terms of cancer. So cancer rates, in that here's a plot of lifetime risk as a function of turnover rate for cells, right? So what's the cell division rate? And this is actually just sort of expressed as total number of cell divisions, but you could think of it as rate. So higher rate, higher chance of cancer, basically. And if you put a line through this, it's roughly maybe 2/3, right? So maybe there's a scaling there that could be understood from a failure mechanism point of view, some kind of, not a simple failure mechanism, but something. It's something we've tried to think about. That's sitting there as, I think, an open question. The problem with this is that it just says, it's bad luck, right? You've got your little cells and doing all the little replicating and crazy things, and things just go wrong. So this sort of story came out, and it's like, well, you can go and eat as much whatever you want, and smoke as much as you want. But if that got a little further away, because it does have a number in here where this is lung cancer and lung cancer. So this is smokers and non-smokers, right? So that's maybe order and a half, a factor of 30 to 100 more. So there are a number of pieces like that where, there's some environmental thing that's happening, and that makes sense, all right? So it's not a do whatever you want situation. It's not just yeah.
I'm just curious on your thoughts of interpreting the residuals of fit when you're on a log scale like this.
Yeah, so I'll have some examples of that. The koala was a good example, right? So some of these things, so if it's just, there's some sort of randomness in the way these things are made, then you kind of hope that there's a nice distribution, Gaussian distribution out around here in log space, and that you could be able to explain that from sort of a growth mechanism. Right? So these things are growing, they're making some errors in how they grow. This is not necessarily this example, but maybe this is organisms and something to do with them, right? So that as you produce bigger and bigger things, there's some fluctuation in how they're produced, and so you get some you get an average trend, right? But you get a variation around it, which on a log scale is Gaussian. So it's going to be Gaussian like this, but of course there's a bigger spread. So usually what happens is, in fact, there's a distribution here and a distribution here and a distribution here. It doesn't have to be Gaussian or log normal. That can be collapsed. And you do that as well, right? So you might want to actually collapse the whole thing. So I'll give you a couple examples in a little bit about cities and so on, where it's quite instructive to look at the residuals, because they're anomalous in some way. And this, if we could collapse if we have a good reason for putting a 2/3 line here, collapse them all down, then we could say, well, relative to its stem cell division, like if we take that factor out, this is the worst cancer, for example, or do that sort of thing. So, okay, well, I'll get to some examples. But yeah, very, very important thing. Often this spread is considerable and needs to be thought about.